Our next talk is by Yura Perov on MultiVerse, causal reasoning using importance sampling in probabilistic programming.
Hello.
Hello.
Setting up the screen. I hope you see the screen.
Yes, we can see it.
Thank you. Hello, I'm Yura Perov. Thanks a lot to the organizers for the conference and for the opportunity, and to everyone for the participation and contribution. My talk today is about MultiVerse. It's a probabilistic programming language and system that enables causal reasoning using importance sampling. MultiVerse was created by me and my colleagues, including Logan Graham, who has made equal first author contribution, whilst we were all at Babylon Health. And I'm currently with Equal, a digital healthcare startup in London, UK. And Logan is going to present the poster later today. And the paper is on arXiv. You can search MultiVerse Perov Graham, for example, or go to this link. And there is also code available on GitHub, including all experiments. And the structure of the talk, I'm going to talk about causal reasoning first and counterfactuals, and then how it lays with probabilistic programming. I'm not going to talk about counterfactual inference in terms of how to automatically derive causal models. And I'm not going to talk about other types of probabilistic models, which are, for example, not directed generative models. I'm not going to talk about discriminative models, in which you also can do counterfactuals, or about hybrids, but that's also a very important topics as well, of course. So how I usually think about this, we have a world, and we obviously limited to how we can perceive and what information we can get about the world, but we get data from the world, and what we can do with this data, we can measure correlations, for example, of different form. And even to measure correlations, you need some model, and you need to start thinking about queries. You can run posterior queries using Bayesian inference, interventional queries, and counterfactual queries. And I personally believe all queries are important, and depending on the question we would like to ask about particular aspects of nature, we need to choose this or that query. And then we do inference once we have the query. And in terms of the model, we usually have some events, processes happening in the world. They might be represented as random variables, for example, x, z, and y. And we usually think there is some distribution over them, and often things are not independent. And then we have some structure, some dependencies, some causal model, and we can do it manually, automatically, for example, using causal inference, or getting help from subject matter experts. So let's say we have this model. We can, for example, consider a very simple model like x, z, and y, where x and z are normally independently distributed, and y is some normal distribution where mean is some function of x and z. But for simplicity, let's assume it's just sum of x and z. And also for simplicity, let's assume that the noise is additive. So epsilon is distributed according to normal 0, 1. And I want to emphasize this additive nature of the noise, because when we work with structural causal models, we need to explicitly mention what exactly the function is, including functions for the noise. And just to briefly talk about structural causal model framework to which we relate this work, there are exogenous variables, and they're usually probabilistic, and there are endogenous variables, and they're usually observable, and they're usually deterministic. I'm not going to give precise definitions as part of this short talk, but for the book by definitions, please refer to the articles and books by Perov et al. So in MultiVerse and for this talk, I'm going to mix in all types of random variables. So we just would assume there is different nodes, and x, z, epsilon, and y are random variables, although y, for example, can be a delta, a random procedure which just takes values of x, z, and epsilon, and just an identity function of that. And for the posterior query, We know how to calculate them in probabilistic programming as well. And yeah, we can use Bayesian inference, for example, exact or approximate. And why we do it? For many different reasons, we calculate posterior observational queries. For interventional queries, and it's a different type, for example, y given do z equal 3, we have a different approach to calculate it. We need to modify the model. So let's say we have a bit more sophisticated model, w and v, and we modify the model, we remove connections between w and v, and we just set z to 3. So that's how we do interventional queries. And why we would like to do it, for example, to understand what might happen if we intervene on some of the variables. For example, it's especially important if it's, for example, unethical to do such intervention in a real world. Again, I assume we have the model and we can intervene in this model. And again, out of the scope of this talk, do calculus which rules allow to transform expressions with do. As per Perov et al., the identifiability of a query can be established by repeatedly applying the rules of do calculus to the query until the final expression no longer contains a do operator, such that the final do-free expression can serve as an estimator of the query, if that's possible, of course. And in MultiVerse, we calculate reasoning, causal reasoning queries given a fully specified model using approximate inference, and we will touch this in a moment. A brief example to illustrate the difference between associational or observational and interventional queries. So here we can calculate probability of lung cancer, so that it's true given smoking is true, but there might be some other factors which affect both smoking and lung cancer. And to factor out this influence of other factors, we can just compute, if we would like to interventional query, what's the probability of lung cancer if we definitely know that we force the patient to smoke, again, in a virtual environment, but it's not because of other factors, it's just because exactly we intervene on that variable, and that is the difference and one of applications of interventional queries. And now for counterfactual queries, we have, for example, a query like this, where we're interested what's the probability of y prime would have been if we have observation on y equal 2, and we had forced one, in this case, y to be z to be equal to 3. We intervene upon z. And to calculate this counterfactual query, we need to do posterior inference over all nodes given evidence y equal 2, and then in that posterior new model with this observation, we need to intervene z to be equal to 3, and then we can predict y prime, what's its value, and it's contradictory to the evidence that y is equal to 2. And there are a few examples of counterfactual queries. For example, we might be interested in a model where there is patient history and treatment and some noise variables, and patient recovery depends on all of this. And we're interested what would have happened, would have a patient recovered if we know that they have recovered, but if they had smoked, if we intervened on that risk factor, for example. And another example is what would have a patient recovered if we know that they have recovered, and if we know some of their medical history as part of observational query, and if we know that they had treatment option A, but if they had another treatment option B as part of intervention, would they have recovered? It's another example of counterfactual query for medical application. So steps to do counterfactual queries, there are 3 steps. There is adduction to get this posterior model intervention, to intervene on this posterior new model, and prediction to get estimates from the posterior model. And usually intervention is costly if you do it in a simple way, because you need to keep this posterior model, which already has new correlations, and you need to somehow preserve it and do intervention on top of it. So in abstraction, it's quite simple, but once we start implementing it, it's not that simple. And we suggested important sampling for inference for counterfactual queries. And I should note that in parallel, similar approach was suggested by Robert Ness. You can see citations in the MultiVerse paper. So to do counterfactual queries using important sampling, we can do 4 steps. We can get proposals from the prior or proposal distribution. You get weights, you apply observations and apply them to the weights, and then you get the intervened samples. So you modify part of the sample where you apply do operator and also propagate these changes to other nodes which depend on those nodes. I will show a bit more illustrations in a moment. And then finally, you use the samples from the posterior world which have been intervened upon with their weights. So it's exactly representation of the posterior world with interventions where weights preserve this posterior part, and then you just do contrafactual prediction by calculating statistics of interest.
Just we have 5 minutes before question.
Thank you. Thank you so much. To provide an example, we have a network and we sample from the proposal distribution, we receive weights, and we intervene, for example, on V, and then we intervene on Z and Y because they depend on V, and then we receive many samples like this and calculate statistics of interest. So in MultiVerse, you can do all of this by using, by having a model in Python, by doing observe and do and predict statements, and you can write generally any Python program. And this is an example of a source code in Python. So you have normal ERPs, and then one of important things in MultiVerse is that each noise variable should be represented explicitly, because usually in probabilistic programming, when we observe, for example, normal distribution or any other distribution, we don't explicitly model this noise variable, but we must for the contrafactual query, and the MultiVerse does it, and you can implement other random procedures, for example, not normal, but some other normal procedure, and that's what MultiVerse allows you to do. So it's not just incorporating it into the likelihood update, but it also represents noise for proper contrafactual inference. And for that, you need to implement inverse function. For example, for normal, it's very simple. It's observed value minus mean value. And you can also have proposal distributions or values because it's important sampling. You can do not just contrafactual queries, but for example, you can do interventional queries, and you can do combination of observational contrafactual queries, or you can just do actually observational queries. There are other PPLs we have, and I'm happy to talk offline about how they relate to MultiVerse, and you also can look into the paper for the relevant related work section. We did comparison with Pyro. Again, happy to talk about this at the poster, and happy to discuss other things like propagation of the effect of the interventions, how to make smart proposal in causal models, how to extend to other approximate inference, and also how to represent different causal models as probabilistic programs in MultiVerse or in other languages. And ultimately, the goal of this prototype is my hope is that these ideas can be incorporated in other more mature and popular probabilistic programming languages like Pyro, Gen, Stan, and others. So I just hope these ideas can be incorporated for fast, efficient causal reasoning. Thank you so much.
Thank you, Yura, for the talk. I have a question. So can you talk a little bit about the experiences you've had trying to deploy counterfactual reasoning in medical applications, and maybe it comment on whether those inform the design of MultiVerse, or what you see as the opportunities for counterfactual reasoning in that domain.
Yeah, it's a very good question. So I personally haven't worked myself on counterfactual inference for medical domain directly. I actually mostly worked on posterior observational inference, on Bayesian inference, how we call it. My colleagues, though, at Babylon Health have worked on applications of counterfactual inference. They have a paper, actually they're also co-authors of mine on this paper, Jonathan Richards, Kieran Lee, and Saurabh Jari, and they have a paper on the counterfactual diagnosis, where they formulate the problem of medical diagnosis as a counterfactual query. And we know examples of medical diagnosis as posterior inference, for example, in QMR and other similar models, but they formulate counterfactual diagnosis as a counterfactual inference and receive interesting results and they do interesting comparisons. So I highly recommend to look into ideas in that paper. And actually in MultiVerse, in the source code, there is an example, a simple example of that, how you can write it in MultiVerse, which happened after they made this work. So you can run this using MultiVerse and see why in some cases it's important to formulate medical diagnosis as a counterfactual problem.
Great, thank you. And one last question from the audience, which is it possible to map MultiVerse from Pearl's do calculus formalism, where it, as you framed it, to Rubin's causal inference formalism?
To be fair, I'm not familiar, I think, with details on this, so I don't know, but I'm happy to talk about this offline at the poster session.
Thank you so much, Yura.
Thank you.